Okay, so we're finally in a position to work out how many photons are going to be landing in a given pixel. We've got this equation here. We know the intensity was about 10 to the minus 3 watts per meter squared for a person 10 meters away from a light bulb. I've put in figures pixel size for my Samsung phone and the F number for the Samsung camera. And that comes out as about 2 by 10 to the minus 17 watts. Not a lot. If you remember, a typical photon energy was about 3.6 by 10 to the minus 19 watts, even smaller. So we're getting about 60 photons per second per pixel. But we don't use 1 second exposure time. It's very hard to keep a camera steady enough for a whole second without a tripod to take a picture. Typical exposure times are more like a 60th of a second or a 100th of a second or something like that. Even if you did manage to hold your camera steady with a tripod, if you're taking a picture of a person or anything like that, it will move in a second. So if we have 1 over 60 of a second exposure time, that's about 1 photon per exposure per pixel. Ooh, well, that's not very much. We're pretty much photon starved. What does this mean? Well, if you're expecting 1 photon per second, you won't always get 1 photon per second. Some seconds you'll get none, some seconds you'll get 2. As we'll see elsewhere in the course, this is a counting statistics problem, counting noise. If you expect n photons, what you will actually get is n with an error plus or minus root n. This comes from some statistics called the Poisson distribution. So what that means is, if you're only expecting 1 photon, you'll get 1 plus or minus 1, so 0 or 2 roughly speaking, which means your percentage error is 1 over 100%. So let's say you're taking a picture of a nice blank shirt. Some pixels will be 100 times 100% brighter than others, which is going to make it look very mottly. Let's imagine you moved someone nearer the light, so they're 10 meters away, so you got up to, instead of 1 photon, you got 100 photons. Now you're going to get 100 plus or minus root 100, which is 10, which is a 10% error. So once again, the pixels of your nice uniform shirt, they should all come out with the same brightness, but in fact they'll vary by about 10%. If you want to get the variation down to only 1%, you need, to say 1 part in 100, you need 100 squared photons, so about 10,000 photons. This is giving us some pretty fundamental graininess. And there's not much we can do about it. I mean, what can we do about it? If we go up to the equation here, you can see the obvious thing to do is make your pixel size bigger. But if you remember from earlier, you need a small pixel size if you're going to get a sharp image. A big pixel size will lower your resolution. People buy cameras because they've got lots of megapixels, and the more megapixels obviously means you've got smaller pixel size to fit them all in. The other thing you can do is make your f number as small as possible, and indeed smartphone manufacturers are currently competing to have the smallest possible f numbers. At the moment about f of 1.7 is as low as they can get. It's very hard to bend the light enough with a sensible lens to get the f numbers much smaller than that. So there's a little room for improvement, but for a small smartphone camera it's quite hard. For a big telescope it's a different factor. For example, the Hubble Space Telescope, the pixel size, instead of being about 1 micron, is actually more like 15 to 18 microns, depending on the instrument, which gives you a huge gain in sensitivity, which of course you need if you're trying to observe galaxies at the edge of the universe. So what we can see here is we have a pretty fundamental problem. The quantum mechanical nature of light, the fact that it's made up of photons, means that in low light conditions, you really need to get a lot of photons to get a good image. And there just aren't enough photons to go around, given the very small pixel sizes and lens sizes of typical smartphone cameras.